Second exercises today will be about mapping the different crop types that are cultivated in the Wallonia region in Belgium. So we will use once again Sentinel-2 images to map the different crops in this region. We map the area using an image from the 27th of June of 2018. And at the end, we will do some analysis also with an image of April. In this area, this is a agricultural area, and the main crop that are cultivated in this area are barley, chicory, wheat, flax, maize, peas, potato, and sugar beet. As I said, we are going to perform a classification, so we will classify the entire area and for these crops, and we will use a classification algorithm. We will use also some a priori information, because for some field, for some farmed areas, we know a priori the crop type that is cultivated in those fields. So we will use the red polygon that you can see in this image. Maybe I just zoom a little bit my screen to train a classification algorithm, and we will classify the entire area. So we can open again QGIS, and we can remove all the layer if you haven't done that already. We are going to use Sentinel-2 image for the year 2018. Therefore, these images have already been corrected for the atmosphere effect. So we are going to see how to import level 2A Sentinel-2 images in QGIS. We, as always, we use the Open Data Source Manager. We can clear the raster dataset line and browse to the second folder, the folder for the exercise 4.2, mapping crop types. We can open the image, the folder that's named S2A for the date 2018 06/27. So this is the second folder in the of the image. In this folder, we open the subfolder granule. We open the folder L2A, image data, and we have three subfolders. One with the band at 10 meter resolution. If you remember, Sentinel-2 has 4 bands with a 10 meter spatial resolution. In the 20 meter folder, we have all the bands at 10 meter resolution that have been resampled to a 20 meter spatial resolution, plus the other band that have a 20 meter native spatial resolution. Therefore, in this folder, we'll have all the 9 bands with a 10 or 20 meter spatial resolution. And we are going to use this folder. So double click on this folder. And we can select all the bands. The bands are the file that end with B, a number, the number of the band, underscore 20 meter. So we want to leave out the first layer, the first file, and the last 3. We are using the 20-meter resolution band instead of the 10-meter because the size of the farmed areas in this region is larger than a 20 by 20 meter pixel. Therefore, we don't need the highest resolution possible of the Sentinel-2 data, but using the 20 meter instead of the 10 meter, we can exploit more bands. Therefore, we have a higher level of detail of the spectral signature of the areas that you are going to classify. Therefore, we prefer to use more band, even though we sacrifice a little bit of the spatial resolution. And we can add all the layers. Now we want to create a single layer, a single multi-band layer, starting from these bands. So we want to merge all the bands into a single layer. To perform this operation, we can go in the menu bar of QGIS. We click on raster. We open the miscellaneous menu and we select the merge tool. In the merge tool, in the first option, we will ask, the software will ask us the input layers, so we can click on the three dots at the end of the line. We select all the layers. But we need to check the order of the band. The last band is the band 8. Because it's called 8A, QGIS set this band as the last one. But this band goes after the band 7. So we need to drag this layer between the band 7 and the band 11. Once you have done it, we can click on the arrow, the blue arrow in the upper left corner. And we go back to the main tool window. We need to flag the option place each input file into a separate band. And in the last line, the merge line, at the end of the line, we click on the three dots, save to file. And we can select the folder where we want to save the output. I'm going to select the folder of this exercise. And I'm going to name the output file as S2 underscore 2018 0627 underscore 20 meter 20 m. We can click on save it and we can run the operation. takes a few seconds. So we are merging all the bands into a single file in order to use it to classify the entire area. Okay, mine is finished. Once it's finished, we can close the window. In the layer panel, we can select all the original bands and remove them from QGIS. We don't need them anymore. We just need the new file. It's taking too long. It might take some time, but it's finished. Okay, perfect.
Okay, for me.
Once again, we need to tell QGIS the bands for a true color visualization of the layer. Okay, someone is still running. Okay, I'll wait a couple of minutes. Okay. Has everyone reached this point? Run the merge algorithm processing. Okay, so we can open the properties of the layer, of the new layer. And it's in the symbology. As before, we need to tell QGIS that the red band is the number 3 and that the blue band is the number 1. At this time, you are looking at a entire Sentinel-2 image. We are not resizing. We have not resized the image, so this is a full Sentinel-2 image, and the area covered by this image is much larger than the area we want to analyze. So we want to to extract our area of interest from this image just to focus our work on the area we are going to analyze. So we need to import a new layer, a new vector layer in QGIS to clip our image. So we open the data source manager, we open a new vector, we can clear the line and browse to the exercise folder. We open the subfolder study area. And we import the .shp file, Wallonia study area.shp. It's a shape file. And we can add it. A rectangular box should appear in the bottom left corner of the image. This is the area of interest for us, for our analysis. In the processing toolbox, once again, we can search for the clip raster from mask layer, so we can search for clip. You should have a recently used option, so we can select the clip raster by mask layer tool. It should be on top. And we can open it. Our input layer is going to be Sentinel-2 2018. I'm sorry, from the 27 June of 2018 Sentinel-2 image with a 20 meter spatial resolution. The mask layer is going to be the only shapefile we have in QGIS, so the Wallonia study area. Once again, we need to flag the option keep the resolution of input raster, because we want our output raster to have the same resolution of our input image. And we can save the image, clicking the three dots at the end of the clip line, save to file. And we can name it just like the full image, just with the underscore clip at the end. And we can save it and run the algorithm. Is someone behind, or everyone has reached this point? Okay. Perfect. We can remove the shapefile and the original image. We can just leave in QGIS the clipped image. And if we right click on the name, the first option is zoom to layer, so we can expand the image to full screen. Now we can import in QGIS the shapefile that contains the training sites for our classification process. Are there any questions? Nice. Okay. We can go once again in vector. We clear the line and we open the folder of the exercise. In the main folder, there is a shapefile named Wallonia 2018 in situ extracted. We open once again the .shape file. And we add this layer. I don't know if you can see the polygons. In my QGIS, they are in purple, they are small polygons. So over the image. If you don't see them very well, you can unflag the image and you see on the screen just the polygons. These are the fields, the farmed areas where we know the type of the crop that is cultivated. So we can look at them just with a right click on the name, opening the attribute table. Here we can see for each polygon represents a field. An ID is just an identification value. In the crop column, there is a numeric value that is associated to the type of crop that is farmed in those areas. In the LC column, there is the actual name of the crop type. There are also some polygons of non-agricultural areas and of grassland, because we want, of course, to classify also those areas, because we don't want to assign to urban areas a crop type, because, of course, there is no crop type in urban areas. The code is just a different number for the classification for the crop type, but we don't really need neither the code or the irrigation column. We are going to use the class code to classify. Okay, so for us, non-agricultural areas have a class code of 7 and so on for the other types. And the last column is just the area of each polygon. Now I'll show you, but you don't have to do it because it's really long, so I'll just show you how to do it, but I'm not going to execute the process, how to convert a shapefile into a training file. A training file is a file that contains the training sites to train the classification process. So to convert a shapefile to a training file, we open the semi-automatic classification plugin. In the band set, that's the first one, the first option in the left menu. The first option is a multi-band image list. The software is asking us which image we want to associate to the training sites to extract the information to train the classification process. Of course, we want to use the same image we want to classify. So if we click on the update on the refresh button at the end of the line, and then in these windows we can select our image. Then we can move to the basic tools window, that is the second one under the band set. And in this window, we select import signatures. Because when we train a classification process, what we are doing is we are observing the mean spectral signature of each class that we want to classify. And the mean signature we are going to compute it on the training sites. Therefore, on the polygon, we are going to observe the mean spectral signature for each class, and we are going to use that spectral signature that you saw this morning, what is, to train the classification and to apply after the classification process to the entire image. Therefore, this process is called import signatures, because we want to import the area that we're going to use to compute the signature mean. In this window, we select import vector. And at the end of the line, select a vector, we click on the green open file. We open the Wallonia 2018 in situ extracted shapefile. And as macro class, MC stands for macro class ID field, we select class code. For macro class name field, we select LC, because LC, if you remember, contains the name of the crops type. And as a class ID field, we can use once again class code, because we are not going to use the class, we are just going to use the macro class, so we can repeat the same pattern, use the same attribute, and the same in the class name field. Oh, I just saw that there was a question a few times, 10 minutes ago. I'm sorry, I didn't see that in the chat. Can you repeat what was the thing you want me to explain? Right. In the meantime, as name field, we are going to use LC once again. Now, as I mentioned, we are not going to perform this operation now, because it takes about 30 minutes, so it's not compatible with the time we have. So if you click on import vector, the software asks you where do you want to save this file, and you convert the shape file into a training file. But you already have provided in the folder the training file, so we can close this window now. I just show you how to do it if you want to repeat with a different shape file. I don't see the question in the chat. Okay, so I move on and I'll come back later. Now we can open the SCP doc. I don't know where you moved it in the QGIS windows. If you don't see it anymore, you can go in the menu bar under View.
Sorry, but I didn't see what did you do with the window, the semi-automatic classification plugin window? Did you?
Okay. I use that window just to convert a shape file into a training file to a trained classification, but we are not going to perform that operation because it's too long. So I just show you how to do it, but it's well explained on the webbook. But you already have the correct file already processed.
So we close it.
Yes, you can close it.
Thank you.
So if you cannot see the SCP doc, you can go in View Panels and flag the SCP doc. If it's already flagged and you don't see it, unflag it and flag it again. Okay. In the SCP doc window, we can select the training input, is the second option. we can click on the green open file, and the file that contains the training sites already converted to train the classification algorithm is the training ROI, when ROI stands for region of interest. So we can open that file as a txt file in the main exercise folder. Yes, an error may appear because as soon as you load the file, it tries to compute the signature, and it might take some second. You should see many lines, pretty much 6 to 7 lines for each clock type. These are the polygons we are going to use to train the classification process. From those polygons, we are going to extract the mean value of the spectral signature. Therefore, the classification algorithm is going to use those spectral signatures to map the entire area that we are going to analyze. So we can flag again the original image. I was leaving it unflagged. And we can open once again the SCP classification window. We can double check that in the band set menu we have selected in the multi-band image list our image, because this is the image that the software is going to classify. Once we have selected this image, we can go in band processing on the left. And open the classification tool. In the select input band set, we can leave the number 1 because we have just one image, therefore just one band sets. We want to use the macro class ID, not the class ID. And as algorithm type, we want to use the minimum distance. It's the one already flagged. We don't need to edit any other option, so we can click on Run in the bottom right corner. And it's asking to select something. Okay, this is an error. I'm trying to understand it.
In the meanwhile, while you try to find out what is wrong, where's the problem, a brief recap. We're using a satellite image to predict the land cover of every image pixel based on the spectral similarity with the spectral signatures of some known fields, of some unknown sites. We have called these sites training sites this morning, and the image pixels included in each polygons are the training samples. So the training samples are used to build a reference spectral model, a reference spectral signature, and all the image pixels are checked with reference to all the reference spectral signatures, and each image pixels is assigned to the class to which it is closer, and this closeness is computing using a distance metric, Euclidean distance. Remember that the spectral signatures that are polylines, spectral signatures calculated from satellite images are first transformed into the feature space. So these curves, these polylines are transformed into points, and that means that 2 points are close or distance based on their distance in the feature space, and the distance of two spectral signatures in the feature space is the distance of 2 points. This is what we are doing now.
If we manage to do it.
Before it told me that I have to select at least one signature. Before
yes, I got the same warning, but we are selecting all the signature. I don't know why it doesn't was working the other day.
Maybe in the third section of the window.
Then cover signature classification.
Okay, maybe.
Yes.
It didn't require it. No, it's not that one. I don't think, maybe, okay.
Was working the last day.
Yes, but they update the plugin every few days, and sometimes something that is working doesn't work anymore after the update.
Sorry, I have to leave. Thank you very much.
Yes. Goodbye.
Bye.
Goodbye.
Francesco.
Yes.
When I run it, the program asked me for a file to save that training or what you are doing. So
maybe it's working then. Maybe for you it's working.
Yeah.
I try to save it in the main folder and name the file as a classification.
Classification, okay.
And we can see if it works for you. If you obtain a classification map.
Extension TIFF?
Yes.
Okay. It's singing.
Okay. So it might be a problem of the plugin that's been updated recently, maybe, because it was working until a few days ago.
I don't know if it's normal, but it's all shed and I can't do anything.
Maybe it's working. Maybe it's just the processing is just.
I think it's running.
Yeah, I think so.
Yes, try to wait.
I have the layer.
Okay.
The multicolor layer.
I don't know.
I can show you mine that I obtained a few days ago. It looks like that. Does it look like that? It's loading, I think.
Like rainbow.
Yes. Yes.
Okay. So maybe I think this is a problem of the plugin that's been updated recently. Maybe you installed the plugin before the update. I don't know.
And you have installed the game this morning.
And
So
I
at the beginning of this afternoon.
Yes. I installed again.
Yes, it could be an issue because a few days ago it was working.
So I can show you my result that I obtained a few days ago, and then I will update the ebook maybe to the new version of the plugin. I don't know, Marco, if this is possible. So the output of the classification process looks like this. Is an image, a multicolor image where we have a legend in the layer panel. So each color here represents a crop type. So we have classified the entire area using the training sites to train the classification process, and we obtain a map where in each pixel of the map has a color, and the color represents a different crop type that is found in this area. If we want to know which is the most farmed crop, we can click on properties on the layer. We can go in the histogram tab that is under the just 200 the symbolic tab, and we can compute the histogram. I know you cannot do that, but you can see on my screen. This is a frequency histogram of all the classes that we have classified. So each class represents a crop type, and we can see that the class number 4 is the most present. This is the class that has the highest frequency. The class number 4 corresponds to flax. So flax linseed is the most farmed crop type in this area. I'm sorry, but you could not perform the classification process.
But they can load the map.
Yes.
Because they have all the processing step, the output of the processing step.
Yes.
Maybe you can show them how to load the map.
Once you run, okay, it's just raster layer, so you just need to import as any other raster. So we can move on to the last exercise. That is a follow-up of this one, where we don't need the classification map to the last exercise, so we can.
So before moving, I hope that now is clearer what we said this morning and why we need training samples and what training samples are used for. Now you see that all the image is classified. All the image pixels are assigned to a class. Of course, this is a prediction because behind the curtains there is a model that assigns a blank cover class based on the spectral similarity of each pixel spectral signatures compared to all the spectral signatures we have defined for training samples. And training samples define the map legend, as you see on the left. So that's why you need to collect training samples for all the land cover you want to map in your thematic map. Otherwise, if you do not collect training samples for some land covers, you will not have those land covers in your map because you don't have any training samples. And so the classification model cannot check the similarity of the pixel spectral signatures to those land covers you did not define through training samples. You don't have any spectral class for those land covers. So remember to collect training samples for all the land covers you want to map. And this is a prediction because it depends not only on the training samples, but also on the classification algorithm you are using. We had no time to discuss this topic, but there exist hundreds of different classification strategies, and each classification algorithm gives you a slightly different output. So this is a prediction of a land cover based on your input data and your assumptions. Okay.
Okay.
Do you have any questions? Can we go ahead? Okay.
Okay. We can remove all the layer from QGIS.
And again, we have spatialized the knowledge of some very specific sites to the whole image in a different way respect to the previous exercise, but we have spatialized this knowledge.
Okay, we can import a new layer. It's a raster layer. So we can go in the data source manager. We clean the line of raster dataset and we import the layer in the 4.3 folder, it's the last exercise. In the Sentinel-2 subfolder, the 10 meter, we select the first one of the two layers, the one from the 18th of April. And we can add this layer. This is a Sentinel-2 image already resized on the study area. And we merged in this image only the band with a 10 meter spatial resolution. Because now we want to analyze the health of the vegetation using the normalized different vegetation index that is computed with the near infrared and the red band. Therefore, we don't need any 20 meter resolution band. So we can use the band with the highest spatial resolution available for a Sentinel-2 image. Therefore, we have imported the image. Now we want to compute the NDVI, the normalized difference vegetation index. And to perform this operation, we use once again the raster calculator. So we can go in the raster menu, in the menu toolbar of QGIS. And we can open raster calculator. the NDVI is a ratio between the near minus red reflectance and the near plus red reflectance. So we can compute the expression. I will compute it and then I copy it in the chat. So it's band 4 minus the band 3 divided by the band 4 plus the band 3. We can save the result in the output layer in the upper right corner. Click on the 3 dots. We can browse to the folder of this exercise and we can save the layer as 2018 04 18 underscore NDY. And we can save it. And we can click on OK to perform the operation. What we get from this operation is a grayscale image, as we saw for the ratio vegetation index in the first exercise. This is a one-band image where each pixel contains the value of the normalized difference vegetation index we computed with the raster calculator tool. Because our goal is to analyze how this index change throughout the year, we want to apply the same index to an image in July, so we can remove the first image. We leave the NDY open, but we can remove the Sentinel-2 image. And we can open the other one. The data source manager, the raster. We click the line and we open the folder of this exercise. We can browse the Sentinel-2 subfolder, 10 meter, and we can open the image of the 27th of June. And we can add it to QGIS. Once again, we can open the raster calculator and we can perform the same operation to derive the NDY. Once again, I'm writing the expression and I will copy it in the chart.
We are writing the formula for NDVI we have seen this morning, but for the Sentinel-2 data, this is what we are writing. And for that specific image, S2 underscore 2018 June 27th.
Exactly. We can save this result too in the output layer. As before, we can call it with the date followed by the NDY, so 2018 06 27 NDY. And we can save it and click on OK. Is everyone at this point? Okay. From the open layer in QGIS, we can remove the Sentinel image. We can leave just the two NDY files. And we can import once again the shapefile containing the polygons with the different crop types. So we can go in the data source manager, vector, and we import the file Wallonia 2018 in situ extracted.shapefile. Now, what we want to do from this shapefile is to extract two different crops. We want to analyze all the 9 crop types. We'll just analyze 2 different crop types, barley and potatoes. So we will extract from the shapefile only the polygons that contains barley or potatoes. And we will observe the different behavior of the NDY for the 2 different crops. So we can right-click on the Wallonia 2018 in situ shapefile and open the attribute table.
Wait a minute, Francesco.
Yes, yes.
Okay, now we can see the attribute table.
Okay. We can select the icon with the epsilon and a yellow rectangle. I don't know if you see on my screen, I'm trying to highlight the correct icon. This tool allows us to select only the polygon that respect a condition we are telling to the software. In the new windows, select by expression, in the green option, in the gray options, we can see in the center of the window. We select, we expand the option fields and values. And we double click on the LC option. The LC string should appear in the left box. Perfect. Now we want to write an equal sign after the LC. So there should be LC between quotes and after an equal sign. In the right bottom box, still white at the moment, we want to click on the all unique. With this option, the software is telling us all the unique values that the LC attribute has in our table. And we want to select, so double click on the barley winter. Now we are telling to QGIS to select all the polygons that in the LC column have the barley crop types. Now, as I mentioned before, we want to select also potatoes, polygons, not only barley. So in the gray option in the middle of the window, we can expand the operator options. And the last one on the bottom, there is the OR option. So we want to select it with a double click. Because we want all the polygons that has as land cover barley or potatoes. Once again, we can go in the fields and values options and we select LC. We are just to repeat the process we did before. We write the equal sign at the end of the line. We click on the all unique once again, and this time we select potato, done early. So we are asking to QGIS to select all the polygons that contains barley or potatoes. And we can click on select features on the bottom right corner. Just to be sure, I copy and paste in the chat my expression, so if you have any warning, you can correct them. And we can select features. And close this this select by expression window. We can see now that in the attribute table, the lines that contains potato or barley in DLC attribute are selected. We can now right-click on the Wallonia 2018 layer, on the name layer, and we can select Export, Save Selected Feature As. We want to export the polygon we have selected and save them in a new layer. Okay. As a format, we want an S3 shape file, is the second option. As a file name, we can click on the three dots at the end and browse to the folder of this size. And I'm going to name the file barley underscore potato. And save it. We don't need to edit any other parameter, so we can click on OK. Has everyone reached this point? We have almost done. Okay, now what we want to do is to extract the value of the NDY for the polygons that we have selected. So we can use the same tool we used in the first exercise, the zonal statistics tool, to extract the mean value of the NDY in those polygons. So we can open the processing toolbox window. And in the search bar, we can write zonal statistics. You should have at the top the recently used tool, zonal statistics. As input layer, we select barley potato. As raster layer, we want to extract first the NDY value for April. So we select the 2018 0418 NDY. As a output column prefix, we are writing 18 underscore 04 underscore. So we remember that these values are from the 18th of April. And in statistics to calculate, we select with the 3 dots at the end of the line just the mean, as we did in the first exercise. And we can go back with the blue arrow. And the last line at the end, with the 3 dots at the end, we can go on save to file. We can save the results in the folder of the exercise, and then going to name the file zonal statistics 1804. We can save it. And we can run the algorithm. We don't need to close the window. We can just in the upper left corner switch back to the parameters tab. We can change the raster layer to the other image, to the other NDY from the 27th of June. We can change the output column prefix to 2706. And in the zonal statistics box, you can just change the name of the file, the last digits. You can change to 27_06. So it's going to save this result in a different layer. And we can run again the algorithm. Now we can close the window.
You see that now we are doing something a little bit different from the previous exercise. We are doing some few statistics on the data.
As the last step of this of today, we can right-click on the last layer we created, the Zona Statistic 2706, and open the attribute table. If we click on the ALC attribute, the table will be ordered by the type of crop, the crop type. We can see that we have the first 5 polygon of barley and the last 7 polygon of potato. We can open the attribute table also of the Zona Statistic 1804. It's the other layer we created. And also order by the land cover type. And we can compare the NTY value, that is the last column of each table, for barley and potato. And we can see that barley is highlighted as a winter crop. And this is also shown by the NTY values, because in April we have high value NTY for the barley fields. It's almost for every polygon higher than 0.8. While in June, the NTY value is much lower, is barely above the threshold of 0.2. That's the threshold for vegetation or non-vegetated areas, as for the NTY index. On the opposite, we can see that potato have a really low NTY in April, is almost under the threshold of 0.2, because we are in early spring, and a high value of NTY in June. So we can tell from this analysis that barley is sown as a winter crop, while potato are farmed as a summer crop. It's interesting to highlight that not all the barley or potato polygon have the same exact value of NTY. This is because each field has different condition, is farmed differently. So there might be a field that is where the vegetation is stressed and needs to maybe to be watered or needs some nutrient. So we don't have the exact same value for all the polygon of the same with the same crop type. I don't know, Marco, if you want to add something else. You have the microphone off.
Yes, thank you. I forgot. So we have finished the hands-on. If you have any question, please ask now, or if you have to think about it, we can also ask later on. Today, we have presented 3 different applications. They are an example of application, but we can use these same methods to do different things. For example, to map deforestation, to map urban expansion, pollution on land, rivers, lake or sea, to map land changes, or to map floodings, landslides, monitor the health of the forest, predict crop production, or anything else. So we have applied the theoretical concepts we have seen this morning. I hope that these exercises were useful to understand what we said this morning. In the ebook, you will find below these 3 exercises, there is an additional resource where you can find again some other examples which are taken from the United Nations Office for Outer Space Affairs, and you can find some 4 additional, yes, thank you. Click on additional resources, please. 3.4.4.
Yes, it's already
okay.
on the screen.
Yeah, you can. Yeah, here we see 4 additional resources where you can find some exercise for fluid mapping and damage assessment, again using Sentinel-2 data, or for modeling coastal floodings, to create maps for disaster preparedness, or exposure mapping, and many more. So these are just some ideas of how you can manipulate satellite images to obtain, to predict, to estimate some numeric values which are related to the biophysical and geochemical properties of the land you are observing, and to transform this information into an ecological information. These are just examples, but we can do whatever you want. Of course, you can also use already available information, and you can mix together or already available maps, but you can also produce your own maps starting from satellite data for your very specific application. I believe that's all. Again, if you have any questions, please ask. We are happy to reply. I hope we were not too much fast in these exercises. The network today was not very good, and we had a delay, a lag between Francesco's voice and his screen. However, any comments, suggestions, and your thoughts are welcome. Yes, I know you are tired. Today was an intense day. Yes, I know.
I just want to say that everything was clear, and today I managed to do everything, so I'm pretty happy with myself.
Thank you very much. It's a great feedback. Thank you. It was, yes, it was intense also for me and for Francesco. It was not simple to put so much information in few hours. Okay, so if you have no comments or no questions, we can say goodbye, and I wish you to sleep well. tomorrow you have the last day. It will be intense also tomorrow, but it is the last day. And so thank you very much for attending, and goodbye. See you soon.
Bye bye. See you tomorrow.
Thank you very much. Bye.
Bye.
Thank you. Thank you. Bye bye.
Thank you.
Bye bye.
Francesco, ciao,
Bye
sono
bye.
Alessandra da